Hi everybody, I'm Abby and this is my project 4. So right off the bat, disclaimer, I did this, I have a little wrong, I have a little bit of an error here. So I want to go through it. I kept it wrong because I think it's just as important to show you all how you could easily make this mistake in the beginning, which would affect everything in the end, and why the mistake is not valid, what should be done differently. So we're looking at populations of Portland and Portland suburbia and how they relate to each other. So these two equations up here, they make sense and they're valid, right? It's just showing, based on the percentages we had, how the two populations are changing. Where I went wrong was not keeping the variables in the same row. So this setup is valid if you're only caring about the first year, right? Because I was thinking, when you do this multiplication of the matrices, you just have to keep straight. Your outputs are going to be flipped from your inputs. And I was thinking, not that big of a deal. It's okay for that first year. But when we go through our steps, and in step 4, you create your generic equation where you hopefully did the substitution and realized that your output population is just your initial population times your percent changes that we called A to the power of how many years it is. The issue is when you put in your initial population, your output is flipped and it's the opposite. Then in the next year, when you put in those inputs that were the outputs, they're flipped. They're no longer the variables you thought they were, right? So what it should be is actually this matrix equation where you need to make sure that your suburban input is going to give you your suburban output, so that when you put the output in as the previous year's input, it gives you the correct output. So it is just a compounding problem that happens after that first year that affected me throughout the rest of the problem. So in part 2, we just wanted to kind of show what this looks like with the graph. My numbers are wrong, but we can still see a trend, the same sort of trend. So these black dots are the numbers that we were given for the initial population, and we can see after that first 10 years there's a big jump, right? And then those jumps start to get smaller and smaller the more years we go up. So those were the ones we got, and I did it for 4 more points. I color coded them on here, so I wanted to show what it might look like, the trends with populations that were similar to each other, very small initial populations, very big initial populations that were the same, and then a population that is, a bit smaller than the other. So you can see in all of these, they have very similar trends where that first jump is big and then the jumps get smaller and smaller. The more years you go up, there's not as much changing happening, right? We're kind of reaching an equilibrium or a steady state, you could say, which is interesting. So as we move on to part 3, this is where we wanted to determine the eigenvalues and eigenvectors for our matrix A. Again, mine's wrong, but your eigenvalues should have actually been the ones right, and then this should have been a positive number, but that's all right. And then when you keep going, here is an eigenvector I got. They should actually be 1.5 and 1. Here's the other eigenvector, and we wanted to see if these eigenvectors span the plane, and we can see that they do because they are not scalar multiples of each other, right? So we can't multiply this by some scale to get that number. So that means that they're not lying on the same line. They're lying more like this, which is good. So they span the plane because they are not linearly dependent. So then we wanted to show how we could write the initial population as a linear combination of our eigenvectors. So I show that here, and using that information, we then wanted to figure out a formula to figure out the population in so many years in terms of our eigenvectors. So going back to our original equation that we came up with right here in the first part of the problem, and then we can make a substitution based on the previous step we had done. So we substitute this in here. We go through, we realize that a to the n times our eigenvector is the same thing as our eigenvalue to the n times our eigenvector. So we make that substitution for a. And when we put in our eigenvectors, because one of our eigenvectors is less than 1, and if we're going off for so many years into the future, so as n is approaching infinity, our eigenvector or eigenvalue is going to get smaller and smaller and smaller, right? So it's actually going to approach 0 as n approaches infinity, which means that our population reaches a steady state, since we just are left with the eigenvalue of 1 over on this side. That means our model is remaining unchanged as n approaches infinity. So we can kind of draw a conclusion from this, that any time you have an eigenvalue of 1, you end up with a steady state model. And that exactly relates to what we saw in our graph over here. I can go to a different example, go to the blue points, which I have to zoom in a lot for these ones. But we saw that our change got smaller and smaller over time, right? As n got closer to infinity, our model was not changing as much, right? This point, there's like 4 of them on top of each other right here. It's remaining unchanged because our eigenvalue is 1 right there. So that's pretty cool. And overall, this problem just helped us see how helpful matrices are, right? Without matrices, we wouldn't have been able to do that step in part 1 where we made a generic equation to figure out our population after so many years. You might have to figure out the previous year's population in order to figure out this year's population, and that would be a lot of work. So matrices helped us do that more efficiently, and helped us also figure out what our model would look like based on the eigenvalues, which we may have not made that connection before. And we saw that after a long period of time, our model will remain unchanged. So it's kind of the cool magic of the eigenvalues and what matrices can show us. So let me know if you made a similar mistake to me, or if seeing my mistake was helpful in some way, so you don't make that mistake on your own in the future. Yeah, have a great night. Thank you.